כן. באמת? זה חדש?
לא יודעת, שאלתי אם זה קורה כי אני למדתי לפני זה במקום שלא היה, אבל אז אמרו לי שכן, כל שנה חופש בעברית.
זה לא היה מעולם, אבל יכול להיות שאולי שיש סטודנטים זרים. אם נתחיל לעשות חופשות בכל החגים, הדתיים והלא דתיים, לא נלמד אף פעם. אני מצידי צריך לבטל גם את החופש בראש השנה וביום כיפור, אבל זה בסדר. אני לא מודע לזה שיש חופש. אני לא זוכר דבר כזה, ואני נמצא כבר כמה שנים פה. אבל מצידי אפשר לבטל את כל החופשות בחגים הדתיים, לא רק את יום כריסמס. חגים דתיים זה לא סיבה לחופש. אוקיי, לא חשוב. So who here didn't read the pages on sufficient statistics in Amir's notes? In principle, it's just like not doing homework. I mean, I can let you go out now, but it's all right. I really want you to read this before the classes. I mean, it will save us a lot of time, and I actually mean what I say. Now, so we are going to talk about, continue to talk about sufficient statistics and information. And actually, this is just so I'm going to complete in the first part of the lecture some deeper notions about sufficient statistics and why I think it's so important. And then we're essentially going to switch pages and move to information theory, but I'm going to do it in a very smooth way, because I really believe that these two things are really highly connected. It's not the standard way of introducing information theory. That's the way I've been doing it in this course for many years, and now I believe that most of the world agrees with me that this is the right way to do it, as it's one of the possible ways of doing it. So it took many years, but that's it. So anyway, so we talk about, again, the Markov chain that we always had in mind, that there's some parameter that generates data, which in general is some sort of an IID sample of size n, from which we generate functions of the data, which we call statistics. And so we had this Markov chain. This is some sort, remember, in parametric distributions, we call them parameters. More generally, we call them world states. In the general Bayesian framework. And actually, I'm going to call them later on the relevant variables. This is something which is a new name for the same thing, but it's actually just a name. I mean, we're going to talk about the things that we actually care about, that we want to know about. And then there is some sort of a channel or George distribution that essentially generates the data given the state. So there's always a conditional distribution there, and at least we always assume that there's also a prior distribution on theta. And this is generally a function of the data. This is what we call, so this is a sample in most cases, or data. So it's conditioned on the state of the world or on the parameter. And this is what we call the statistic. So this is just a little funny name, but that's how it's called. I mean, it's a function of the data. It, by the way, can be a noisy function of the data. I mean, this can also have some sort of a distribution here. It's not necessarily a deterministic function. But at least at this point, we still think about it as a deterministic function of the data. And we actually said that S is in some sense sufficient. So we had a definition of what I call sufficient statistic. So S of X, let me eliminate the N now just for simplicity, but we always think about a sample of a large set of data, so X can be a very complicated measurement. It can be IID, it can be not IID, but something we can actually measure. So if S of X is sufficient statistic for theta, and this is it's always for something. Sufficiency is not an independent quantity. It's sufficient for a given parameter, for a given relevant variable. It's sufficient for theta, or it's S sufficient statistic, or whatever. For theta, this, by the way, can be multidimensional, just as theta can be multidimensional. So it can be many functions like this, not just one. It's a vector function. So S of X is sufficient statistic for theta if there are several definitions which are all equivalent. The probability of the data given S and theta is the same as the probability of the data given S. So the likelihood when I know the statistics and the parameters, so all of these are equivalent. I mean, this is one possible definition. If I'm a Bayesian, I can write it, the probability of theta given S and X is the same as the probability of theta given S alone. So in some sense, these two are equivalent through Bayes' rule. It's very simple to see. So if I'm Bayesian, I'm allowed to write the probability, the posterior probability of theta, then these two are equivalent. You can easily check it. And so essentially it tells us the intuitive thing that everything that the sample has or the data has about the parameter is contained in S. So if I know S, there's nothing in X that tells me more about the distribution of theta. And then I actually said that an equivalent definition is that not only this Markov chain holds. So this Markov chain is a natural one. I am in the state of the world, or I have some given theta. I generate data, and then I calculate the function of the data. So this is obviously a Markov chain, because this is a function of this, and this depends only on this. So if, in addition to this Markov chain also holds, which is theta S. Actually, maybe you should write it like this. I mean, so there are arrows here, but the arrows are usually bidirectional unless said otherwise, S and X, which means that these are all equivalent. So 1 is equivalent to 2, which is equivalent to 3. So those are all equivalent definitions. Okay? Sorry? Yeah, I can write in any direction. It's actually undirected graph, but if this is a little bit more intuitive. I mean, so I can predict theta from S alone. I don't need X. So this is essentially the meaning of this inequality. So you can think about the arrows. So far, this was the natural arrow, but unless I say otherwise, you can revert these arrows in some sense. I mean, it depends on. In more complicated graphs, it's not so simple to reverse the arrows, because there's an underneath notion of causality, which I don't want to get into, not at this point. Who was first, in some sense, and who caused what? So sometimes we associate with those arrows some sort of causal relationships, but at this point I'm not talking about causality. So you can think about it this way or this way, but this equation actually tells you this way. I mean, you can infer theta from S alone. If I add X to it, it doesn't add anything. So all these three definitions are equivalent. You can derive this from this and this from this if you are a Bayesian. Okay? So essentially a sufficient statistic is a statistic where these two Markov chain holds. Okay? This is very important. So sometimes we're going to use it later to characterize. And then we had a theorem or a lemma, which is the Neyman factorization lemma. Fisher Neyman factorization lemma. As you already know, lemma are usually more important than theorems in the sense that they actually give you the essence of the thing. And theorems are usually some sort of corollaries or some conclusions that come from lemmas. But usually they are supposed to be more important. But in this case, just like it's the Neyman-Pearson lemma, Neyman liked to write lemmas, but it turned out to be very important. So this was that an equivalent definition, actually. So all those are actually equivalent to the fact that there exist functions a and g such that the likelihood of the data, again, when I say x now, I actually mean a sample, a large piece of data. The likelihood of the data is can be written as, can be factorized as a function of the data only times the function of the data and the statistics. Now this looks like a very naive thing in some sense. I mean, okay, first of all, it's clear, so 4 is equivalent to 1, which is equivalent to 2, which is equivalent to 3. So these are all equivalent definitions in some sense. But this is not so obvious. Why is it true that if this holds, then this is indeed a sufficient statistic? But you can easily, or not so easily, you can check it. And I don't want, as I said, the proofs are in the paper. That's why I want them to read them and understand them. I'm not going to ask about proofs like this in the theory in the exam, but I certainly want you all to read them and try to understand them. If you don't understand them, let me know. It simply takes too much time here to prove it. But one direction is actually very easy. That if this is true, that 3 or 2 implies 4, it's very easy. The other direction is slightly more complicated. You need to break the states of observation and talk about into partitions, which depends on certain value of the statistic. And there you actually assume that the statistic is a function and not just a stochastic function, but you don't really need to assume that. So there are actually several proofs of these theorems which makes different assumptions about S. Now, if this is true, so first of all, this is a very useful way. First of all, it's clear. So this is, as I said, is an equivalent definition. Essentially, Neyman Fisher gave us another definition of sufficient statistic, which actually, in some sense, is much more practical. It's easier to test in many cases. So if I can factorize the likelihood, this is the likelihood function. Likelihood. If I can factorize it in such a way, then S is sufficient. Now, it's quite clear that it's not a unique way. If there exists one, I can always multiply it and divide it by any function of the statistic. So give me some function of the statistic, f of s. So I can divide it, multiply and divide by f of s, and then put this into h, and this into g. And of course, because s is a function of x, h times f of s is also a function of x. So this is so obviously this is not unique. I can always modify f and g by any function that I want. So it's not a unique factorization. And actually, the notion of sufficient statistic itself is not unique, of course. Any one-to-one function of a sufficient statistic also is a sufficient statistic. So I can take any function of so for example, I can take an estimator and turn it into something which is not an estimator by a one-to-one function, and it will still be a sufficient statistic. A sufficient statistic is a much more general notion than estimator or efficient estimator. An estimator, I mean something which is actually estimating the parameter, is if it's efficient and so on, it's also a sufficient statistic, but it's not necessarily, doesn't have to be an estimator. It can be anything. That's why it's a more general notion. Okay? So efficient you saw that if they are efficient, they obey the Cramer-Rao equality. And then I showed you the actual exponential forms. And I'm going to argue now that exponential forms are exactly and precisely all the distributions that have exact sufficient statistics. So in some sense, efficient estimators are always sufficient statistics. Yes? Sorry, yeah, of course. Yeah, theta and S. Yeah, sorry, this is a typo. An important correction. Theta and S. Okay? So the dependence on the data, the thing that actually connects theta and the data is S. So of course, if you have this factorization, you already know that usually, so for example, so this is a theorem, okay, I didn't prove it. As I said, one direction is actually very simple, check for yourself. The other direction is slightly more complicated because it goes through, I need some more assumption to have a simple proof. I actually prove something much more general than that later on. So I keep it at this point as some sort of an exercise for you. Try to prove that all these four things are equivalent. Of course, use the notes. Because this one direction here is not entirely intuitive. Okay, so convince yourself. Now, so even without talking about minimal sufficient statistic or anything like this at this point, this already tells you something quite nice. So for example, maximum likelihood estimators are functions of sufficient statistics only if such exist. So this is very easy because I showed you actually last time. So you take the log. So the log likelihood is of course the log of age plus the log of g of theta and s of x. And then you know that the likelihood equation or the maximum likelihood estimator, so theta ml is the thing that minimizes is the argmax of log p over theta. Okay, this is just definition of the maximum likelihood estimator. But this maximum is a solution of the equation that the derivative of those, which is essentially the argmax. This is again a little maybe strange notation, but the argmax of this set, the set of solutions of the likelihood, what we call the likelihood equation. So all the thetas that satisfy that. Okay, the set of theta that satisfy that are all the solutions of the likelihood equations. If it's unique, then it's unique. We take the one which actually maximizes the over theta. It's not argmax over theta. It's the it's in the set of this. Okay, this argmax belongs to this set. Okay, but this set depends only on g, not on h. Because if I take the derivative of the log, this does depend on theta. So this function depends only on this. So those theta can be, it's exactly the same as the derivative of g, theta s, to d theta. Okay? So h doesn't come in. The only way the data comes in is through s. So which means if you're going to solve this equation, the theta maximum likelihood is going to be a function of this. Essentially just extracting theta out of this derivative. Is this clear? Obviously not. Okay, so essentially what I'm saying, look, the solutions of these equations are exactly the points where they are included, at least because they're also minima maybe. So they are part of the sets of this set, and this set depends only on g. That's what I'm saying. because if I take the log and take the derivative with respect to theta, this is 0. And this is the only thing that matters. Okay, so, and actually this is true, and you can show it yourself. It's also true for theta map. This is easy. And it's also true actually for theta MSE. So all these three priors that we play with all the time, delta, square, and also true for the median. It's true for essentially all the things that we talked about so far. Okay, so but what is really nice about the Neyman factorization is not only that, it can actually find the statistics. What are the sufficient statistics in some cases? Just by looking at how they factor, how the likelihood factorizes. Yes?
I think I'm not clear under which condition this factorization holds. Is it general or is it...
So what I'm saying is that 4 is equivalent to all these 3.
So if the other 3 are holds,
all of them hold together. 1 implies 2, and 2 implies 3, and 3 implies 4, and 4 implies 1. They're all equivalent. Yeah. If you're Bayesian. The only thing you need to allow me is to have a prior over theta. If you are not Bayesian, then you cannot go from 1 to 2. But if you are Bayesian, then you can write it, and that's it. Yeah.
Do you mean the minimum statistics?
No, I'm not talking about minimals now. Any sufficiency.
You're saying it exists. You know that it's always exists.
That's right. So in some sense, it's a triviality. You're right. So if S is really not simplifying the sample at all, then the whole thing is a triviality. So S being the sample itself is always a sufficient statistic, and that's what we call a trivial sufficient statistic. So it's still not a contradiction. All those relationships will hold also for trivial sufficiency. But you're absolutely right in that we want interesting sufficient statistics in some sense. That's what we are going to talk about next. But yes.
What does it mean that theta is conditional?
It's not condition, this is a set. Okay, so I need to, so when you define the set, whatever, I don't, the set of all the people that have a salary higher than 1,000 shekels per month is defined like this. I mean, okay, so you've said, okay, all the objects, this is just a condition of the object, and here there's some condition, okay, so on X. So when I say this notation is a set, it's the definition of a set. So this can be anything, in principle. I mean, all the houses with red roofs, all the people who are polite in this class. I don't know, whatever. Of course, those of you who learned a little set theory, I hope some of you did, know that I cannot really put any condition there. Okay? You haven't heard about it? For example, I can have a set that includes sets of sets. For example, the set of all the sets is a set. Okay, so I can have a condition that whatever here. But then, of course, you run into paradoxes. I mean, if you never heard about it, you should have. So for example, I can have something like the set of all the sets that include themselves, or the set of all the sets that don't include themselves, and then I run into Russell's paradox and the Elias paradox and all those things. So it's actually very important. So we can't have, in general mathematics, it's not healthy to have sets that can include themselves, that they can be a member of the set. So the set of all sets is not really a legal thing. It has what's called self-reference, and self-reference is a problem. And if you don't know that, you should know that, even if it's not part of this course. And whenever you have something which refers to itself, you usually run into paradoxes. And I mean, this is really the origin of most paradoxes, like the Elias paradox, Russell's paradox. Essentially, all the famous paradoxes in mathematics are some versions of self-reference. Actually, what you should know that also questions like, do I have free will, or does God exist, or all these kind of questions are self-reference. They're essentially paradoxes. They're all paradoxical. So it's actually important for us here. Okay. Yeah.
So I'm not sure
Yeah, so that's what I'm going to show now. So essentially, I'm saying that the Neyman factorization lemma is actually giving us a very practical tool to find sufficient statistics. And we actually showed it already in the case of Gaussians. So first of all, okay, so this is actually important it's for important notation. This is the definition of a set in set theory. It's a set of objects that obey some conditions. But while I said that, I mean, I just wanted you to remember this is one of the most exciting fields of mathematics, set theory, which really leads very quickly to a lot of interesting questions, including paradoxes. So and some of those paradoxes are actually relevant from brain science. Okay, yes?
Excuse me, I missed something here. So what's the relationship with spectral vacuum and the math and why you mentioned the other two?
Why did I mention this?
No. Math and MSE.
No, what I'm saying that theta maximum posteriori and theta MSE also, if there exist sufficient statistics, are a function only of the statistics. For the same reason. So maximum posteriori is easy because it's again derivative. For maximum MSE, you have to work a little harder, but it's also true. So in some sense, sufficient statistics, if we can find non-trivial sufficient statistics, then they're actually going to tell us something very interesting. And that's exactly where I'm going in this class, in this lesson, in this lecture. Okay, so I said already, and you asked me again, I mean, so I said that the factorization lemma is giving me a tool. So for example, let's say that we have the simplest possible distribution I can think of, the exponential family. Okay, so the exponential distribution actually. So e to the minus theta x, and what is the normalization here? So x is positive, non-negative. Real, non-negative. And what is the normalization? Theta. Okay, good. Okay, so this is a family. This is called the exponential family. It's actually a bit confusing. This is called the exponential distribution. Exponential family is much more general, but this is the simplest one. So what is the likelihood? So again, I need to think about samples, IID samples. So this is the likelihood function of the sample. What is this going to be? This is a product. So it's going to be of theta e to the minus theta xi. Okay? So this product, which is theta to the n, e to the minus theta sum xi. Okay? You didn't cheat? No. Sorry. So, you multiply this n times, you get theta n times, and you get the sum of the exponents, the sum and the exponent. Okay? But now I look at the Fisher factorization theorem, and I say, okay, the only thing, actually h here is trivial, is 1. I don't need h. The only thing which actually contains x, the sample, is this sum. So if I think about it as h times g of theta, h of x times g of theta and x, this is again xn in this case, I see that h is trivially 1. I don't need it in this case. And this is g. This is g, and I see that this particular x, sum over xi, is a sufficient statistic. So I see just from this factorization that the only functions, this particular function, theta to the n, e to the minus theta, is a function of theta and this sum. So I see that the only thing that I really should remember, so this particular sum in this case is a sufficient statistic, because it obeys the factorization lemma. It's a trivial factorization, okay? But it's actually important. So the sum in this case is a sufficient statistic. Of course, also the mean. I can divide it by a constant. It doesn't make any difference. Okay, so of course you know already that in this case, this number, which is a function of the sufficient statistic, is also the maximum likelihood estimate. And indeed, it is a function of the sufficient statistic, which is the sum. Okay? Actually, it's much more general. If I look at the exponential family, so if you remember the exponential, this is the exponential distribution. The exponential family was something like this, which I can always write as some function of x over some normalization, never mind, e to the minus sum of some functions which may depend on the parameters, some other functions which may depend on the data. So this is just another way of writing what I call the exponential forms. So the exponential forms, I actually wrote it as a log of p equals some function of this can be a function of theta in general. So you see that this may be more familiar form for some of you, I hope. It's, I mean, for example, the Gibbs distribution in physics or the things like this always have this particular form. This is what we call the exponential form. So any exponential, this is not n, I'm sorry, this is some k, some function of the data. So in this case, the dimension of the statistics is actually k, but okay. So in some sense, this is our generalized exponential form. Is this clear? I mean, is this clear? This is equivalent to what I wrote last time, which was the ln p is some function of lambda r, theta, some function of the parameters, some other functions of the data, plus might be, I call it c of x plus d of theta. Okay. So in this case, c of x is ln p0, and d of theta is minus ln z. But this is the same thing. Okay? So writing it in this form and writing it in this form is exactly the same thing. And this is what we generally call the exponential forms. Okay, so exponential forms are either you take the log, you don't take the log, and you call them with whatever names you want. So in this case, there's some prior modified by this exponential factor. And we actually saw this already very early in the course when we started to do things like decision or sequential decision making or hypothesis testing. We actually had exactly this time the Bayesian update was always multiplying by something which changed the distribution in this way. So this is, in some sense, a very fundamental form.
Why do you have the minus?
Just for convenience. I can change, I can write the lambdas anywhere I want, okay? It doesn't change anything. There's a convention to put a minus there because those, I'm going to show you later on today, these lambdas are actually some sort of Lagrange multipliers. How many of you, by the way, don't know what Lagrange multipliers are? I really need this notion today. All of you heard about it. Okay, so eventually I'm going to show you that these numbers are going to be Lagrange multipliers of when I maximize the entropy, but this is later on today, okay? So that's why I put a minus. It doesn't change anything. I mean, the definition here is arbitrary. I mean, this was any function. Okay, so I actually from here on I would like to use this notation because in many cases I want those to be positive numbers, but it doesn't really matter. If you think about the Gibbs distribution again in physics, A is the energy, and this is going to be the inverse temperature. For those of you who heard about it. Okay, so this is a special case of an exponential form. Okay. So now I'm going to use the Neyman factorization to show you that what happened here is actually happening in all the exponentials. It's actually very simple. It's the same proof exactly, I just repeat it. So the likelihood of the data is what? Is again the product. I'm talking about IID. That's the only assumption I'm making here. You can relax this assumption, but it's making things a little more complicated. But of course, we will eventually. So for IID samples, this is just again a product. I go from 1 to n. So I is the index of the samples, and R was the index of the statistics here. So I go from 1 to n. Again, the probability of one sample of one of the sample points. This is always true. for IID. So make sure that you know that it's not always true. It's true if it's IID. And then what? Then I get exactly the same thing. I get a product of P0 of xi divided by z of theta to the n. Let me write it like this. And then I get the product of the exponents, but I can put it again in the exponent. So it's e to the minus sum over this lambda r of theta. Sums, so this is a sum over the statistics, and this is a sum over the samples of AR of xi. And now you look at the Neyman factorization lemma, and you identify this as H, and this as G. So in this case, G. If this is G, because the parameters, okay, yeah, sorry. I have to include the Z. I cannot do this. So I take the Z and put it here, minus ln Z and ln Z. Okay, sorry, this is wrong. So this is H and this is Z. And you see, this is a function of the data only. You see why I could put the ln Z there? No problem. And this is a function of theta and the statistics. But what are the statistics now? They are precisely those sums. Okay, so I see from here that those sums of AR xi, this particular set, is a sufficient statistic. So this is a proof using the Neyman factorization that for exponential families, the sums of those functions that appear in the exponent, or those functions that contain the data in my factorization, are precisely the sufficient statistic. So this is a very simple generalization of what I wrote here. Is this clear? Okay, so for example, in the Gaussian case, which is a simple case of this, the two functions that appear in the exponent are x and x squared. And therefore, this function are going to be xi and xi squared, which means that the first two moments, the empirical mean of the x and the empirical mean of x squared are sufficient statistic for Gaussian. This is a very simple. Together they're sufficient statistic. In the case of Gaussian. In the case of Gaussian, we already saw many times that in the exponent there are only two x and x squared appears in the exponent. If I open the square, yeah. So the first two moments are sufficient statistic for the parameters of Gaussian, mu and sigma. And we know that, of course. Of course, we can rearrange them in terms of the empirical mean and the empirical variance and many other things, but it's the same thing. We don't have to. Okay, so you see already that exponential form, this is actually a proof. Once you believe in Neyman's factorization, this is actually a proof that all the exponential forms have sufficient statistics. And they are precisely the empirical means or the sums of these functions. Yeah. I don't want to write it as a theorem, but the nice characterization is that this is true also in the other way. If there exists sufficient statistics for any, which the dimensionality of the sufficient statistic, in this case it was k. There are only k functions. And k doesn't grow with n. If k doesn't grow with n, so the dimensionality of sufficient statistics is the same as it is fixed, it doesn't grow with the sample size, then only exponential forms obey. And this is a very famous theorem, which was really a very big disappointment in the statistical community in the 40s, which is called the Pittman-Koopman-Demois theorem, which essentially tells you, okay, sufficient statistics are very nice ideas, it's a very nice concept, but they exist only for very special distributions. Which distributions? Precisely those that we so love and already saw, the exponential families. That's it. Yes? It's a function of the data. No, if I divide it by n, it's empirical mean. No, but yeah, as I said already, that sufficient statistics are defined up to one-to-one functions. Okay, anyway, it doesn't change anything. So dividing by n is not going to change anything. So essentially, these are the up to factor of n or factor of 1 over n. It's a function of the empirical mean. So we usually think about it as moments. So these are some generalized moments. Or we write them like this. I mean, AR. And in physics or whatever, we call them the empirical means. Empirical means or empirical moments. Now, of course, you see already from here that this is unique only if the ARs are independent, are linearly independent functions. So you know what are linearly independent functions? So I cannot write a non-trivial linear combination of them, which is 0. Okay? So this means that if they are dependent, I can actually reduce the dimensionality of the statistic. I can to the minimal set of independent functions. That's also an important lesson. Those of you who didn't quite get it, keep it there. Okay, so as I said, this actually turns out to give us another equivalent condition, and this is really the sad story. Another equivalent condition for the existence of exact sufficient statistics which are non-trivial. And what I mean by non-trivial, the dimensionality of the statistic doesn't scale with the data, doesn't grow with the data. In that sense, they're not trivial. So they can't be just a whole sample, something like this. And this is only if and only if P x theta is of exponential form. And this is called the Pittman-Koopman-Galois theorem. Yeah.
The condition you said that the dimension is finite or
independent of n. Actually, it's an open question, a very interesting open question. If I can extend this to things that grow with n but slower than n, let's say log n. So there's a conjecture, I mean, it's not mine, that you can actually always find something which is essentially sufficient statistics as long as the number of statistics grow with the size of the data, at least logarithmically. But that's a different story.
So you're saying like a statement that this equivalency is true, but the condition includes something.
The condition is something more tricky.
Can you say that without using something that is in the statement?
Yeah, you're absolutely right. You point your finger on something very deep, and I'm going to get into it later on today, after the break. and that's there's something fishy about this definition of non-trivial sufficient statistics, because in principle, I mean, those of you who know some mathematics, I can encode any number of continuous function in one continuous function in a one-to-one way. There is a one-to-one map from Rn to R1 to the 0 and 1 interval. So in some sense, this notion of the dimensionality of the statistics requires some refinement. I need to give you some more. And indeed, in the proof of Pittman-Koopman, there is an assumption, and it's a very strong assumption, that those statistics are differentiable functions of the data. I didn't want to get into this proof. As I said, I mean, there's actually a sketch of the proof in the Hebrew book of the course. Amir omitted it, but it's still there. And those of you who really want to know about it, it's full. The literature is full of the proofs like this. Actually, it's a very tricky. Of course, so if I am assuming that it's also a continuous function in some sense, like the moments, like x and x squared are continuous functions, okay, then the dimensionality is settled. I cannot do this trick of mapping all the high dimension function into one interval, one-to-one. You know, all these clever set theoretic maps that show you that the Rn is equivalent to the 0-1 interval is a kind of self-reference in some sense. I mean, it's a funny statement, but it can be done because they both have the continuous power, the power of aleph, as we say. Those of you who don't know what I'm talking about, again, it's not important. Okay, so again, so there's something tricky there. And actually, I'm going to show you later on today that actually boils down to a much deeper concept, which is the notion of information. So I'm going to characterize sufficient statistic another way, which is through the concept of information, and that's why I'm exactly making this transition. But there's another interesting characterization, another interesting nice property of sufficient statistics I want to mention in the 1 minute that I have. And this is called the Roe Blackwell Theorem. Again, those of you who read the notes, so the Roe Blackwell Theorem is telling me something interesting in statistics. So actually, I think that it comes from some misconceptions about. So the statisticians really never really, as far as I'm concerned, never really completely agreed with, or completely, let's say, okay, I don't know. Maybe not. I shouldn't say that, but statisticians usually don't give that much importance to sufficient statistics. I think it's very, very important. And especially not. But the Roe Blackwell Theorem theorem is telling me that if I have a sufficient statistics, then I can always improve the variance of my estimate, or the MSE of my estimate. So if you're, let's say that theta hat from the sample is an estimator of theta in some parametric family. So essentially, and S of xn is a sufficient statistic of theta, for theta. Okay, so you know what I mean by this. Maybe this is not very nice, sufficient statistic. Okay? So, so what? So then the MSE, so the theorem is that the MSE of theta hat given the statistics cannot be larger than the MSE of theta hat alone. So this is the theorem. The theorem tells you that if you know a sufficient statistics, then average finding the mean square error, and you know this is the bias square plus the variance. If it's unbiased, then it's only the variance, and so on. So finding conditioned on a sufficient statistics, this and S, yeah, S was missing. If and S is a sufficient statistic, then I can only condition on a sufficient statistic, I can only reduce the variance. So in some sense, good. If you have a sufficient statistic, take it into account, and you improve the minimum square error of your estimator. Yeah, no. So which means that if I actually obey the bound, then I'm already a function of sufficient statistic. That's essentially what it tells you, because you cannot improve it. So this is actually the beginning of the proof that an MSE, optimal MSE estimator is a function of a sufficient statistic. Because then if I condition it, otherwise I could improve it. So this is called the Raw Blackwell Theorem. I don't want to prove it. Actually, Amir has that proof in his notes. It's not so important. You can read it there. Yes?
What does it mean that the estimator is conditioned on the...
So remember, the MSE of an estimator was defined as the expectation with respect to the data theta of what? Of theta hat minus the theta square. This was definition. Now, when I mean conditioning means that, okay, so condition your distribution not only on theta but also on S. If you condition also on S, if S is sufficient statistic, you can only improve the MSE. That's what it is. So this conditioning is actually going to narrow the distribution of the statistic in some sense, to make it, if it's an unbiased estimator, then it's simply going to reduce the variance. If it's biased, it's going to reduce somehow both the variance and the variance, or either one of them, or somehow reduce the sum. they change the statistics. I'm averaging over a different distribution.
But the estimator stays the same. So
No, but this is the mean. Okay, so the mean over all samples. So this is the function of all the samples, not just one value of the estimator. So the distribution of the estimator is going to be narrower, in some sense. I'm not sure what's not clear. So this MSE was an expectation over all samples. Okay? So it's the expect minus theta, the true theta is what I mean here. Okay, so what is the squared deviation from the true parameter? Now we broke it into the variance of theta hat given theta plus the bias of theta hat given theta squared. That's what we already showed. And what I'm telling you, these two things, the bias, it was the average. So this is the average of all samples. Now the question is, from what distribution do you take the average? Over what distribution you average? You can average over only the distribution of the data. But if you know a sufficient statistics, you can only decrease. So in some sense, it's a triviality, but in some sense, but it's triviality when you know more. But this looks like a very useful theorem. I mean, if you have a sufficient statistic condition on it, and so can only improve things. Okay, no, we're out of time. I want to move to more interesting things. So next, in 10 minutes, I'm going to start talking about information, and then I'm going to give you a completely different characterization of sufficient statistics, which actually captures this intuition that the sufficient statistics captures all the relevant information about something. And this is going to be the beginning of a very exciting story. It's really what I call it's the main part of this course as far as I'm concerned. I mean, the notion of why information is such a valuable and important quantity, and how can we use it for many other things like understanding the brain. Okay, so stay with us.
הקטע שיש לי נגיד כל המדגמים השנתיים, ואז אני מחלקת את זה לסטטיסטיק סטטיסטיק, ואז במקום לעשות תוחלת על הכל, אני עושה על סטטיסטיק בתוך
בדיוק. או שקראת את זה או שהבאת לבד, זה בדיוק הרעיון. הרעיון זה שאני מצמצם את עצמי למיצוע רק על השטחים שבהם סטטיסטיק.
קודם אני חושבת נגיד את הממוצע של המדגם שלי, ואז אני כל המדגמים עם אותו ממוצע.
בעצם הרעיון הזה של סטטיסטיק הוא חלוקה, דרך לחלק את המדגמים. ככל שבהם הסטטיסטי קבוע, יש לנו סוג של פרוסישנינג של הדאטה, והמינימום של הסטטיסטי יחזור לשכל, כמו החלוקה הגדולה ביותר. אם אנחנו מבינה את זה, מה אתם?
סתם, כאילו, אמרת, זה היה נקדות הרוסי, מה שאמרת על פונקציות אחת חדרית, כאילו, מכירה את הקוונטות של השקילות בין אחד ל-RN, אבל לא הבנתי איך זה.
אוקיי, לכאורה אני אמרתי, יש כאן מספר סטטיסטים מספיקים, לא? שהמימד שלהם זה K. עכשיו מישהו יכול להגיד לי, כיוון שאמרתי, כל פונקציה אחת ערכית של סטטיסטים מספיקים, גם סטטיסטים מספיקים. אז כל המימד הזה זה מין רברי, כל הפונקציה זה פונקציה אחת.
אבל זה
כן, אבל זה אומר, אני אמרתי גם משהו שהדימנשן של הסטטיסטי, או של הקרמטר, אוקיי. אבל כבר, יכולתי לשאול את זה כבר כאן, כי אני יכול לקחת אותה את ולייצר בהם איזה משהו חדש, ואני אקרא לו new bar, שהוא בעצם מקדם את שניהם. המשפחה הדו-פרמטרית הפכה להיות משפחה חד-פרמטרית. זה כל הסיפור של הממד של הפרמטרים דורש איזשהו רפלמנט. אם עד כדי פונקציות חד-חד-ערכיות, אז בניגוד עם מתמטיקה שפונקציות חד-חד-ערכיות זה פחות מפות עד Rn ל-X1. אז אני קצת בבעיה. הבעיה שהפונקציות האלה מאוד מאוד לא רציפות. כל הפונקציות האלה של מפות נושא R2 ל-R1 הן לא רציפות. אז אני מקבל סתירה לכאורה למושג הזה של ממד. באמת ממד של מרחב רציף הוא באופן אינהרנטי מותנה באיזושהי חלקות. באיזושהי תכונות טופולוגיה שנשמעים. ולכן אני חייב להניח שבאמת אני באיזשהו מערכת התוצאות של ה-X אחרת כל ה-X. אבל X לא חייב להיות משנה רציף. אז זה קצת variablen
In
kunnen.
exponential function you have normalization.
Vom letzten Stelle vermessen das schon, das ist genau.
Okay. So usually it will be only sum of the value.
Maar als je afstellen.
Another function, part of this form.
Okay.
And when you write it, now you understand why it's correct.
Okay.
Fine?
Thank you. Thank you. Thank you. Have you finished Markov theorem?
Finish. Just started it.
Which question and
4. Started.
Four.
Yes.
Oh, four.
4.
Okay. Yeah, I'm also in four. Yeah, maybe we can do it together. Yeah.
Yeah, you can do it after the class.
对，我感觉这东西很 trivial，对，我感觉这个东西有点。
是吧？就讲说，对，这个这是一眼看得出来的。
为什么这个一眼看不出来？
如果我看到这样一看，我会认为，我会看得出来，对，就是这个它是一个方式。我很好奇，就是它本来，对，这个是很难看出来的。我是有点看不出来，它是当它其实是的一个方向，怎么一个也是个方向，但是。
这个东西，我看到那个 note，他只写这个东西，他没解释为什么。在今天写的时候，
他说没有。
应该是没有的。我看到那个。我自己写错了。
Yes, you want me to bring it to you?
然后这个东西是这个东西，他把
It's a bit odd, like it's like it would have been someone that way. Yeah, everything's like.
这个然后他就拿这种东西代替了，就把这个东西放到这里来。
I think he told us that he used 5 but yeah.
然后他就把
No, that's okay. You can remind me so, but I'll try to remember. Yeah, no problem. It's kind of like but you don't need all of it. You don't need all of it. Just part of it.
How are the distribution effects? You need to read
In the exam?
or you need to read under the thing?
这个 note 我确定我看过的。
I went over the slides.
Under the thing?
I had some notes that Mo made for some of the chapters, but not all of them, which were very good. I can ask her to send it to you. And that was very detailed, like she really explained everything there, but she didn't understand half of it.
实际上就是说那个
mentioned like
exponential
things.
Okay, but maybe I will so you can bring the
Yeah,
distribution.
sure.
对，但是我
I studied this mainly from the book.
Yeah.
And YouTube, kind of studied. You didn't use it so far?
No.
So if you know that any concept you don't understand, they are like the best at it to everything. Yeah, for biology in particular, it's really good because it like show you.
Yeah,
show
show you how to
yeah, so definitely I use it a lot. But yeah, we use the book as well. It's really good. When is the exam? Before the end of the semester, usually like a month.
Yeah. At the end of the
Yeah. You also have, actually it's better for you to do it.
yes, thanks.
It saves you a lot of time. you have also when you get it like
Yes.
right? It's doing like exam. No? Noga? And get it במהלך תקופת בחינות? It's doing the exam. No?
No,
Or ask it when?
yes, it's changed.
It's changed.
I think
But
it's
then,
after, but I will check.
because last year it was.
Yeah, I didn't have that.
But they changed it because they made the semester break longer.
Oh, so it's in my mילואים?
I will tell you.
What?
When is your Halloween?
From the middle of from February to the middle of March.
So on the 11th of March. It's on your Halloween?
Yeah.
What do you care? We don't even like it.
I like free.
Food?
Because I don't have if I do not have anything to study, so it's better to be in the lesson and to be able to go. So yeah, so it's better if you don't have time.
Okay, so we want to continue.
No. לעשות את המיקום שלכם.
I don't want to Okay, I must tell you that I actually got many good questions. This is a good sign. Yeah. Once you ask questions, then I understand that something goes through. Yes. I'm sorry, I didn't hear.
Define conditions on something which is not distributed. For example, if the condition on the first observation,
Yes.
will it not also
No.
include it?
No, not necessarily. No, I mean you can condition on things which actually create bias, increase the bias. Condition on things which will completely distort the distribution. I mean, depends on. So it's not obvious. It's not completely obvious. Look at the proof. Okay. So the proof, as I said, I mean it's 5 lines, but I don't want. I'm already behind schedule as far as I'm concerned. If you can read the proofs yourself and understand them, it's fine with me. If you have questions after reading the proofs, bring them here. Proofs takes time. That's the only problem, and you always make mistakes when you prove it on the board without looking at your notes. Okay, so but this particular notion, so I was asked in the not now, but more. What's so special about these moments? I mean, the sums of. So first of all, notice that we not only show that the sums of the A's over the sample are sufficient statistics, but this is a very special, a very nice kind of statistic. This is an additive sufficient statistic in the sense that when I get new data, all I have to do is to update this sum with the last point. So in some sense, I can, when we start to talk about processes and behavior and things like this, or memory, the kind of things that I need to remember in this case are only those running averages or running sums. So when I get new data and want to update my knowledge, I only have to update the sufficient statistic, and I always do it by adding the last point. So moving from n to n plus 1 is just adding another point to my sample, which is just updating those means in some sense. And in physics, for example, we sometimes call these kind of things empirical average or expectation values or observables. I mean, we usually use the terms observables for these functions in physics. And I don't know how many physicists are there, but if you saw in quantum mechanics, for example, these are the kind of things you actually measure. things like, momentum, energy, location, things like this. And these are usually correspond to some sort of operators over some space. And these are the kind of things that are going to appear here. And so in some sense, there's something very deep here, which goes all the way to the notion of measurements and the notion of getting things about the world and so on in those sufficient statistics, if we can actually have sufficient statistics which are finite dimensional. Now, this whole notion of dimensionality, as I said, is tricky if I just limit myself to one-to-one functions, which can be discontinuous or non-differentiable, then dimensionality falls apart completely. But if I assume some sort of continuity or differentiability, then the dimensions, the whole notion of dimension in geometry depends very strongly on the assumptions about continuity and differentiability of functions. This is just a general thing that you eventually should know, at least some of you. Now, Loga actually asked me something important which I wanted to say. So essentially, sufficient statistics or any function of the data generate a partition of X. Okay, I said it already last time, and this is actually very important. So a partition of X is, I'm using the Noga's drawing. So this is X. Let's say this set is all the possible X's. Actually, if it's a sample, then it's an n-dimensional Cartesian product of X, whatever. And this is and a partition is some sort of a coarsening of X. So the statistic gets, let's say, value S1 here and S2 here and S3 here and so on. So in some sense, it can break the sets of all X's into pieces for which the statistic has the same value. So for example, if all the samples for which the mean is 0 there are many samples, let's say of Gaussian variable, that the mean is 0. They can only, so all of them collapse into one point in my statistic. So this partition, so S is actually a partition. Partition of X. Of Xn even. And if it's a finite dimensional partition, I mean, it's a finite number of values, it doesn't refine with n. And then it's a non-trivial statistic. And then we said something last time, which is actually more non-trivial. Not only non-trivial, we would like to have the simplest possible partition. So what I mean by simplest possible partition, so if you give me any partition, let's say this one, and I can coarsen it by eliminating these internal partitions, and essentially still get a sufficient partition, then it's coarsened. I mean, I got so it's a function of the previous partition. So a minimal sufficient statistic implies the coarser partition of my data, which is still sufficient. Okay, so this is something I want you to remember. I actually said it last time. So a minimal sufficient partition, let's say T, is going to be minimal if for any other sufficient statistics, it's still a statistic, but it's this Markov chain holds. Which means I can, well, it should go this way, but I don't. I can still refine it. It's still coarsen it, not refine it. Coarsen it means eliminate or merge together parts of X which are distinguished in the finite statistics but indistinguished in the coarser statistics. Okay, so this is some sort of a very abstract notion. I want to quantify it, and so at the end of the next lecture, which is Wednesday, for those who don't know, I'm going to essentially give you a completely different definition, which is using the notion of mutual information. But for this, I need to build some other things, yeah, some other concepts. Yes.
The definition of S1, S2, and so on. I don't understand why is it sufficient. I mean, I cannot generate the data from.
You're not sure. You shouldn't generate the data. You should imply everything about the statistic. Yeah. So there's something wrong, by the way. I mean, really a conceptual mistake in Amir's notes, where he said, in fact, not only in Amir's notes, in many statistics books, that in principle, if you know sufficient statistics, you can sample and generate another sample using only the statistics, the value of statistics.
There, the number 3, right?
Yeah, but that's true. I mean, so this particular chain rule, Markov chain, is true for the specific data on which you actually calculated the statistics. If you are trying to use it on new data, it's not true, because new data can improve your statistics. So this is strictly speaking true only in training, or on the training data. That's a very important point that I think is wrong in not only in Amir's book, in Amir's notes, in many statistics books. This is true as long as you don't generalize. But if I actually get new data, if I want to sample an equivalent sample to my own sample it given the value of statistic, which means you already constrain yourself to a certain estimator, but then you are not going to generalize well out of this sample. So it's really tricky. But yes, again, if S is sufficient statistics for all samples, then this chain should always hold, which means that if I know the value of the statistics, I know theta, but I don't know theta. I know theta just in the sense that I can imply everything that the particular sample gave me about theta from the statistic, but I still don't know theta. I have a distribution of the theta. So it's again a question of what do you mean by resampling your data. If you sample the distribution of a theta, then essentially you generate an equivalent sample on the basis of what you saw in your training data. I'll come back to this when we start to talk about learning more specifically, after we talk about information. So learning and this notion of generalization and out training and in training, all this is very tricky, and you really have to. So here it's already coming up in a somewhat confusing way. I mean, if you calculate, you get a data. Let's say I get a sample of 10 points from a Gaussian distribution. I calculate the statistic. I obviously don't know the parameter. I know the parameter up to what this sample allows me. Now, if I sample the data condition on these statistics, I will get, only if I average over all number of parameters on some sort of average sense, I will get a correct estimation. But given this particular statistic, I don't have the true distribution. I have some sort of an estimated distribution. Okay, again, this is a very good question. If you notice that, then you're in good shape. Okay. But so this is really a mistake that I have to point out about the notes. There are many mistakes, of course. There are many mistakes in our notes as well. Okay, so now I'm going to erase this part, isn't it? I'm actually going to talk about this word now. The beginning of a formalization of this notion of information. Okay, so there are many ways of doing it, and there are many books, and if you find different books, give you different ways. So essentially, you know, the anecdotal, the how would I say, colloquial or everyday sense of information, the word information is very loaded. And so it's of course a very important word in language which existed way before it was formalized mathematically. So when we say information, it's still very confusing to a lot of people, especially people who come from humanities. And why do I insist on quantifying it in a very precise way? So you have to, in some sense, forget the usual meaning of the word information. We're going to give it a very concrete meaning, which may or may not coincide with what some of you think about the word information, and may or may not capture some of the other meanings of information in the everyday sense. So essentially, the way we want to do it now follows in some sense the notion Shannon's information theory. Actually, information theory is a very confusing word. So Shannon, Claude Elwood Shannon, in was one of my heroes at least. But during the Second World War, he was at Bell Labs, and he was actually asked to think like many others at that time. Actually, it's parallel to Turing, who did more or less the same thing during these years between 1940 and 1945, but in England, 1939. So they had to think about the notion of encryption and communication, efficient communication. So actually, the right name, or the correct name of this is the mathematical theory of communication. But I think that Shannon already, some people had already the feeling that they're talking about modern communication. But eventually it was reduced historically, especially by the electrical engineers who took this field and as if it's their own private business, and back into this limited, rather restricted notion of information, which is in communication theory. So, but Shannon was actually thinking about communication. And he was thinking about a very simple mathematical mode of communication, in the sense that how is information transferred or moving? What do we mean by information in general? And how is it communicated and moved from one place to another? So I'm going to sketch to you in several lectures here, something like 3 or 4 lectures. We're running out of time. I mean, we have only 6 warm weeks. So we have to, and if next week we are not teaching, then it's a problem. I have to squeeze another lecture somewhere. But so I'm going to sketch the whole theory, but I actually want to claim that it's actually much more general, and that's why I don't want to start with communication. I want to start with the notion of sufficient statistics. And we already see, I mean, that some funny things pop up here. I mean, for example, these exponential forms are very, very important. And this notion of measurement is very, very important. Well, what do I actually get from data? We saw it in many different places. Yeah, by the way, I forgot something very important. I mean, you can use the Neyman factorization lemma and apply to the decision-making problem. If you remember, the Bayesian decision or the sequential decision. And you can get, it's a very simple exercise, and actually, I don't know if Ravid gave it to you, but I'll ask him to give it to you. You can use the Neyman factorization lemma to show that the log likelihood ratio, the log of P1x over P2x for 2 states of the world, is a sufficient statistic for the question of what state of the world I am. It's actually a minimal sufficient statistic. It's actually a very simple exercise once you saw what we said before. I mean, write the probability of the state of the world, posterior, as a function of the data, and you see that the only thing that really comes into it is the log likelihood ratio. So using the Neyman factorization problem lemma, you see from that the log likelihood ratio is a sufficient statistic. I'm actually going to argue that it's a minimal statistic. And we already saw this. So as I said, I mean, this notion of sufficiency and minimality and relevant information, all these things need to be clarified. What do I mean by this? So the first question that Shannon actually asked himself, if I have a random variable, yeah, of course, and there are many, many books on information theory, and actually I always recommend people, especially at your level, to go back to the original paper of Shannon, which is 1948. This particular very classical paper called The Mathematical Theory of Communication, or it was very modest, and I called it A Mathematical Theory of Communication. And this paper, by the way, was written over many years. I mean, it was actually the first version of it we know now was appeared in 1942 in a very different context, in the context of encryption during the war, and it was immediately classified as a secret paper which should not be published, and because it referred to the notion of encryption and how safe is encryption and so on. And it's actually, he called it the mathematical theory of secrecy, of secret communication, or something like this. This paper was released to the public only in 1960. But then he wrote a public version of it, an unclassified. Actually, of course, worked a little more since 1942, between 42 and 47, and he wrote this really classical paper on the mathematical theory of communication, which introduced many new notions: uncertainty in the variable, the entropy, the commutation information, the notion of the channel capacity theory. Everything was there. It was really a complete new theory which was put in one paper, and of course it was not accepted to any journal because nobody can swallow so many new things together. So it was actually rejected from all the important journals in statistics, and eventually it was published in the Bell Systems, as a technical report, Bell System journal, which was essentially an unreviewed. That's like putting on the archive today. I mean, actually, I believe these are the best publications usually. Those that are rejected from everywhere, probably, if they are deep, I mean, they have the chance of being very important. Very important papers usually don't pass reviewing. So this is actually a very classical example of a very important thing which was rejected from everything. Now, X random variables. So if there is a random variable, Shannon asked, is there a measure of the uncertainty? Uncertainty of X. What should it be? He actually even called it, he didn't really know how to call this function. And Shannon unfortunately didn't know enough physics. So he said, okay, let's call it U of X. Uncertainty. It's not his notation, but actually this is a good notation. Because I want to distinguish it from what I'm going to call it later. And so this uncertainty of X, he wanted, okay, what should I require from an uncertainty? So it was clear to him that this U of X, uncertainty of variables, should be actually a functional of the probability of X. Which means if X has a probability distribution, then it must depend on it. So the probability of the distribution should tell me everything that I know about how. So this is a very strong assumption, by the way, that everything that I really want to know about a variable is captured by the probability. I already mentioned it in the first class, if you remember, that we need to convince ourselves that probabilities are really inevitable in some sense, and it's not entirely true. It's true only if you restrict yourself to real functions, actually, as we know now, and quantum mechanics has a slightly different version of uncertainty, which is very, very different. So everything you want to know about a variable is not captured by the probability, but something else, which we call the density function or the complex amplitude. So those of you who know something about quantum mechanics, so this is really already a very strong assumption that is not always true in physics. But for us, the probability of distribution of a random variable captures everything you want to know about it. Of course, conditioned, unconditioned, whatever. So he wanted the function of the probability distribution, and he wanted essentially. So let's say that X. So he immediately restricts himself to some discrete variable. Let's say that it takes some n possible values, some discrete variables. And then he said, okay, the uncertainty should be a function that depend on distribution in a way which will not change if I branch or if I break the variable into pieces. So let's say, okay, so intuitively said, okay, if I know if the distribution is very sharp, it's picked on one value, then I have no uncertainty. Okay? So there's one value. So the uncertainty should be 0 if the distribution is what we call singleton, or is on one value, delta function. Okay, so this was one intuition, actually the very first one. And on the other hand, if this is true, when is the most maximum uncertainty? When it's uniform. Okay. So he said, okay, first of all, if it has a finite number of values, the most uncertain distribution should be just 1 over n, 1 over n. So the uncertainty of the distribution 1 over n for a discrete variable or the uniform should be larger than the uncertainty of any other distribution of X. This is the maximum uncertainty. And the minimal uncertainty are the single forms, which means the corners of the simplex.
Oh, here, trying to estimate some parameters?
No, we're not talking about parameters now.
What to be certain about?
We are not talking about parameters now. We're talking about variables. Okay. Parameters are special case of variables, which are going to abolish at some point and replace them with something much more interesting than parameters, but it will take some time. Okay.
What I was trying to get.
So what Shannon tried to get is some function that characterizes the uncertainty of a variable. And he said, okay, it must depend on the distribution. For example, if the distribution is uniform, then I have maximum uncertainty. That was a very clear intuition. If the distribution is less uniform, I know more.
Why did you focus on discrete?
No, I can do it for non-discrete, but it's easier for discrete. That's what Shannon did. Now, so there are many functionals of a distribution which will be maximized for uniform and minimized for single terms. For example, the sum of p squared. The sum of pi of px squared over all x's is a function like this, which will be maximized if they are uniform and minimized if it's single. Check it. Okay, so there are many functions that are monotonic in that sense. So he didn't like this because there are many other options. So then he asked something much more interesting, and that's assuming that I reveal the uncertainty in two steps. So let's say that x can get these n values. So I take x and I break this into what I call x1 or x2. So the values of x can be branched into two distributions. So let's say, for example, I have a die which can have the values 1, 2, 3, 4, 5, 6, okay? And then I'm actually throwing it. I cover it for you. Okay, and what is your uncertainty about the value of the die? So a priori, you don't know anything. You have a maximum uncertainty. All the possible 1, 2, 3, 4, 5, 6 are equally likely. But then you can break it and ask, okay, if I'm asking you, is it even or odd? Give me an answer to this question. So essentially what Shannon was really inventing, in some sense, in a very clever way, is this notion of revealing the uncertainty by asking questions about the data. And let's say that instead of asking what is the number on your die, I simplify my question. I first ask you if it's even or odd. And then you tell me it's even. Okay, you give me, is it even? I said yes. Okay, so it's a binary question. This started to become very important. It's a binary yes or no question. And somehow I want this one question is somehow so I know it's even. So I know it's either 2, 4, or 6. So in some sense, you would say that you would like that half of the uncertainty is removed. Okay? Because you actually shrank your space to half of the values. So in some sense, said, okay, if I break my variable into two sets, the values of my variable into two sets, I remove the uncertainty in steps. I first ask, is it in this set or in this set? This is one question. In this case, it's actually what we call a binary question. It's a yes/no question. And if the answer is yes, then the uncertainty that is left, okay. So you should ask something like, I know it's already even. So is it 2? Okay. Or is it the all powers of 2 in that sense? No. Is it the power of 2? Okay. So 2 or 4. Or is it divisible by 3? I don't know. There are many questions you can ask. So essentially, you can remove the uncertainty in some sort of a tree of questions. Okay, and this was already very much in Shannon's mind. So you all know, let's say, the 20-question game. Yeah, this is something I cannot avoid. So let's say I'm choosing a number between 1 and 100, and you can ask me only binary questions, which means only yes/no questions. Now, you have to reveal the number. Initially, you have uncertainty of what? Maximum uncertainty. All the 100 numbers are equal, because I didn't give you any prior, I didn't give any preference. And now, what essentially Shannon was coming to is what is, in some sense, the number of binary questions, or the minimum number of binary questions that you must ask me in order to reveal the number. So essentially, this was already very much in his mind. But say, okay, so let's say here there was an uncertainty of x, of complete x. Here, at this point, I have an uncertainty of this set, let's say even or not odd or something like this, and at this odd this set. So you gave me an answer here, yes or no. So it has some probability. Let's say in the case of even odd, it's half-half. But I could actually ask you, is it 1 or 2, or 3, 4, 5, 6? In this case, we'll have a probability a priori of third and two-thirds. Okay? So I split the data into two groups. This will have, let's say, probability P1, and this will have P2, which is 1 minus P1 in this case. Okay? And then I would like to say, okay, the uncertainty that I have left after giving me an answer to this question should be simply the average of these uncertainties plus the uncertainty removed by the question. Okay, so he actually formed it as some sort of an axiom. I'm doing it very, very slowly, and I have to go much faster. So he formulated that the uncertainty in X should be the uncertainty in P1 and P2, which is 1 minus P1, whatever it is, which is how much I actually removed by giving you an answer here, plus the average sum of Pi uncertainty of Uxi. In this case, I go from 1 to 2. Okay, so this he actually formed as an axiom. He wanted the information to be additive if I remove it by branching my data. So this is actually called by Shannon the branching axiom.
What do you mean by the first term? P1?
Yeah, so whatever, this is distribution. It's a distribution over this binary variable, which was the answer to my question. So it has an uncertainty. I mean, uncertainty must be a function of a distribution.
So that's my initial guess?
No, so he said, okay, this must be always true. However, I break the variable x, let's say, into two pieces, the uncertainty of all x should be the sum of uncertainties are removed. So the first uncertainty is removing if it's here or here. This is this uncertainty. And then whatever left is the average uncertainty. Yes? Yes, in this case they are disjoint. I mean, it can be either this or this.
Like it's only added if they're disjoint.
If they're not disjoint, I have to modify. I can do it, but I have to clarify what I mean by that. It can be both in both of them. And then what do you mean? Okay, did you remove an uncertainty or not? So of course, if you have two sets, let's say 1, 2, 3, and 3, 4, 5, 6. So if I tell you that it's in both of them, I actually gave you a lot of information. So, but this is actually meant them to be disjoint. So this is okay. So at this point, Shannon introduced a function. So then he wrote this axiom, which is called the branching axiom. Branching axiom. Not everybody likes it. And then he showed, again in his first paper, that if I want a function, a general function, which is a function of a distribution, so any distribution, so you can, and then he called it actually H, P1 to Pn. So this is, in this case, in the discrete distribution, it's the distribution of all the possible values of x. So he wanted this to be a functional, it's called a functional because it's a function of a function. It's a function of the distribution. And he wanted it to be essentially, okay, if I group it to the first part, to obey the branching axiom. And then he showed, which is something I'm not going to show, again, out of lack of time, it's actually, again, a very instructive thing to read it, that the only function which obeys the branching axiom and is continuous with respect to the values of P. If I change P a little bit, it's continuously changed. And that's all. Must be proportional, must be of the form of this form. Okay. So he said that essentially it has to be continuous in one point. If I change p around 0, it's enough. So in some sense, he said, okay, the only function that obeys the branching axiom is a general function of the distribution. I can calculate it from any distribution, and obeys and otherwise unlimited. I can be anything. Is this function, and the log can be taken, so it's proportional to this function, which essentially is like choosing the base of the log.
Also the maximum certainty.
Yeah, you're right. You also need the fact that the uniform distribution has a maximum uncertainty. This will just select the sign, and the singleton has a minimum uncertainty. So this was actually somewhat of a surprise to Shannon. It's pi, I'm sorry. Pi, and I is the index of the variable here. I goes from 1 to n. Okay, the values. Now, in general, okay, this was for discrete variables. Discrete, finite values. It can be easily extended to infinite values, but it has to be discrete for this to be true. I mean, to extend it to continuous variable, we'll have to work much harder. And then, so Shannon actually really proved this theorem that asking this very simple requirement that you are continuous with respect to the uncertainty of the distribution and so on, and you obey the branching axiom, this is the only function that obeys this. And then, Shannon, this was in the mid-40s. He had a very good friend at Princeton University, which was not that far from Murray Hill where he was. And his friend was a guy called John von Neumann. Maybe you heard about him. If you haven't, you should have, because he's probably one of the most important scientists of the 20th century. So actually, John von Neumann, together with Albert Einstein, moved from Germany to America as refugees, essentially. And they were both Jewish, and both didn't get a position at Princeton University. Of course, nobody said that it was Jewish, but they found all sorts of excuses why they shouldn't get a position at Princeton University. And eventually, they formed a different institute for them, which is called the Institute for Advanced Studies, IS, and it's still there. John von Neumann and Albert Einstein were the first two members of this institute. And anyway, von Neumann did many things, including establishing many of what we know now about computers, and many of what we know now about quantum mechanics and other things. And he eventually died when he was less than 50. But at that time, Shannon came to him and told him, look, I discovered a wonderful function which seems to characterize uncertainty in a very beautiful way. What should I call it? And then von Neumann, who knew some physics, told him, physicists know this function since the 19th century. They call it entropy. They never understood what it means. Call it entropy. Okay. And this was actually the beginning of a long list of confusions and misconceptions. But since then, this function is called entropy. Now, as some of you know, entropy was invented in the 19th century in the context of thermodynamics as this mysterious thing that happens to matter when it swallows heat without raising the temperature, like in phase transition. And so it was some sort of the part of conservation of energy, which we understood that in order to actually formulate the conservation of energy, we need something new. And this something new was very mysterious because some systems could increase the disorder or uncertainty in some sense, and the energy could get into entropy without increasing the temperature, which was a very strange thing for people in the 19th century because they thought that temperature and energy are very closely related. So how can it be that I swallow energy without increasing the temperature? And this was essentially the reason why Clausius and Carnot and all those who formed the thermodynamics in the 19th century, when they thought about heat engines, invented this funny function which some of you may have heard of, called entropy. Now, Shannon came from it from a completely different perspective, thinking about uncertainty in variables, which will, as you already begin to see, will lead to the notion of a code. And those of you know what I'm talking about. And it turns out that the same function, exactly the same function, the sum of p log p, or the expectation of the log of the probability, minus the log of the probability, is exactly the same function that Boltzmann and later Gibbs used in the 19th century to characterize statistical physics and thermodynamics. And since von Neumann knew that. He told me, look, this is entropy. Boltzmann called it entropy. Gibbs called it entropy. Why do you want to call it something else? Okay. So I'm going to call this function the entropy of P. So the entropy of P is just the beginning of a very exciting story, which eventually leads us to the notion of information. But I really want to already make a very clear distinction between uncertainty and information. These are not the same thing. So entropy, so I just make a definition. Formally, the entropy in the random variable x, which I denote like this, is defined to be minus the sum over all the possible values of x, whatever they are, of px log px. And you see that there is a choice of which log to take. I can take a decimal log, I can take a natural log, I can take a binary log. So there's some base here. But this base is just going to change everything by a factor. So we usually think about a as greater than 1. So this is a monotonically increasing function. And this will only be a change of units in some sense. So when we put 2 here, binary log, we measure these things in what we call bits. So this is going to be bits if this a is 2, or base is 2. Okay? Let's call it b, base. Okay, so, and of course, if it's going to be lambda, it's going to be different units. In thermodynamics, actually, the base is something else completely, which is called the Boltzmann constant. But so it's a very different number, has a completely different dimension, but then it's going to turn this into units of energy over temperature. Now, so this is a funny function. It has some very nice properties that we already saw. It obeys the branching axiom. So I just want to sketch some of the properties of it. First of all, it's maximized for uniform distribution. Okay? So if P, so one property, so I'm going to prove all sorts of things about it. One, age of the uniform distribution, let's call it unif, like MATLAB. The uniform distribution of x, if this is 1 over n, so what is it going to be? So all the numbers are 1 over n. So this log n. Okay? So of course minus is log of 1 over p, and 1 and otherwise minus log of 1 over n is log n. Okay, so log n, so this is indeed increasing with the dimension, and this is the maximum. Okay? Now, okay, so let's try to understand a little more about it. So first of all, and by the way, if it's a singleton, which means it has a single value, what is it? So age of a singleton, when I say singleton, I just mean one value, okay? 0. Why is it 0? So log is 1 is 0. Yeah, and you need to be a little careful here, because 0 log 0, it sounds like a funny thing. But, okay, so indeed it's 0. Because I assume, or I can actually prove that 0 log 0, whenever you see something like this, this is 0. Now, of course, you shouldn't believe me. So you take an epsilon log epsilon, and take the limit where epsilon goes to 0, and this is indeed 0. And if you don't know how to prove this, come to me later. Okay, so 0 log 0 is 0. Now, so this is nice. It has these two properties. So let's, and it actually obeys the branching axiom.